of memristors and memristive devices. Lecture 3 was memristor circuit and systems. Yesterday we talked about neuromorphic computing, history, and what neuromorphic computing is about. Now we are ready for how to use memristors for neuromorphic computing, in particular for artificial intelligence, machine learning. And at the end, I like to share some maybe potential scenario for brain scale neuromorphic computing. Is it possible? Maybe difficult, but at least we can discuss such a scenario. So, you know, everybody is talking about these days GPT-4 or next version of it. GPT-3 required 175 billion parameters. GPT-4 is almost 2 trillion parameters. So these are parameters for learning, right? So it's related to all the weights in a deep neural network. And you have to train for test patterns and set values, all these connection weights. And that takes a tremendous amount of time. In fact, in GPT-4 training, the cost is to train GPT-4, $100 million for training. Tremendous amount. In terms of energy requirement, is 1.3 gigawatt hours. So it's a nuclear power plant to train such a deep neural network with so many parameters. While Moore's law is progressing only like twice every 2 years, or about 2 years, the modern AI, they progress almost 100 times, 10 times per year. So if it is a 6-year period, if not million, it's at least 500,000. Whereas in 6 years, Moore's law will progress only 8 times. So there's a huge gap between the Moore's law can do and what application demands. So how do we narrow this gap? And that's how we suggested maybe, among others, a memristor can play some roles. It doesn't say that the memristor will solve it, but at least it can contribute significantly. So that's the motivation for memristors in neuromorphic computing. Now, people also talk about computing in memory, right? Or in-memory computing, the CIM or IMC, or in-memory processing, IMP. So the tremendous bottleneck, a power wall, and then the speed wall happens between a processing unit, which contains on-chip memory like SRAM, and then memory external to the chip, DRAM and non-volatile memory like disk type of a thing, huge memory. And usually what happens is for Neumann architecture, you do fetch data from external memory into chip and you calculate, and then you push it back, store it, and then come next cycle. If you need additional data, you bring it back, processing, and then store it back. So back and forth over this long bus, which is very costly. Idea near memory processing is try to shorten this distance between processing chip and the memory. You short. So such as here, you have processor here, you bring it close together, high bandwidth memory system, or stack together, make it close, right? So that way capacitance in between will be reduced. Or you stack memory on top of a processor. But better yet, processing in memory, PIM, or computing in memory is distributing memory function into processing unit, DRAM, SRAM, non-volatile memory, etc. So you do computation within the chip. Thereby, you cut down the need for traveling back and forth. Now, next slide will explain more quantitatively. So again, you do have processing unit, right? You have a control section, arithmetic logic unit here, usually called the register and the ALU here, data path we call. So you have on-chip cache, and then external memory. So you have to give a back and forth between this long distance bus, meaning that the high capacitance. Power, at least in the I/O, power is bus capacitance, VDD square, and the clock frequency. So in this particular case, example is a 24-bit long per clock cycle. Whereas if you do processing on memory, moving this processing function into this memory here, then you do a lot of processing here, computation here. So you don't have to move it as frequently. Maybe just a command signal you need. So say command signal is only 4-bit long per clock cycle, then you have a factor of 6 difference here, at least. So in simple analysis, I/O power saving by doing in-memory computing is a factor of 6. And in terms of what elements you can use for on-chip memory, yes, you can have a SRAM, or you can have embedded DRAM, you can have a flash, embedded flash, or resistive RAM, phase change memory, or spin torque transfer, magnetic RAM type of thing. You have all this sort of choices, right? So that's sort of a advantage of computing in memory processing, or in memory computing. So people use CIM, IMP, IMC. It's all same thing. Data bus bottleneck, right? So this shows some experimental data. So if you have a CPU, processing unit, and the memory, and if you have a bus, depending on memory size, and then access to the data in the memory. So if it is 8K memory, access energy will be 10 picojoule, 32K memory, 20 picojoule, 1 mega, 100 picojoule. If you have to go DRAM, huge DRAM, maybe 1300 picojoule, even 2600 picojoule. In terms of computation operation, 8-bit integer multiplication is 0.2 picojoule, addition is 0.03 picojoule. 32-bit integer is 3 picojoule, and the addition is 0.1 picojoule. 16-bit floating point, 1.1 picojoule, addition is 0.4 picojoule. 32-bit floating point multiplication, 3.7 picojoule, 0.9 picojoule for addition. So you can see that multiplication takes far more energy than addition, right? So you will see later on in a large language model, my colleague here at Santa Cruz, Jason Ashragian's group, developed a large language model that does not require multiplication. So you can just remove this the energy amount, which save energy tremendously. So that's an interesting aspect. Now, this shows some circuit operation, logic circuit operation in memory, computing in memory. So, suppose you have a memory, SRAM memory, but modify the SRAM with 8 transistors. So this is a traditional 6 transistor SRAM, right? Static random access memory. You have an inverter back-to-back and the access transistors, right? And bit and the bit line bar and the word line and so on. And then this is excess transistors to external world. So this has a 8 transistor unit. And consider how you can do logic operation with the memory. So you have a cell 1, which is this whole thing. Another cell 2, this is the whole thing repeated here. And then, yeah, you have a, so actually this one is this cell 1 is a 6 transistor cell, 6 transistor. And then this is repeated. This is repeated for cell 1. So 6 transistor cell 1. And then this one is a M1, M2 here. 6 transistor cell 2. And the M1, M2 here. Right? So if data here is A, data here is B, then 0, 0, 0, 1, 1, 0, 1, 1 combination. For NAND operation, no operation, this is what you expect. NAND is 0, 0, NAND is 1. 0, 0, no is 1. 0, 1, NAND is 1. 0, 1, no is 0. 1, 0, NAND is 1. 1, 0, no is 0. 1, 1, NAND is 0. 1, 1, no is 0. So how can you realize this NAND no operation in this circuit? So this is just a simple buffer. So practically this no value here is the same as here. No, NAND value here is the same as here. This is just a buffer. Right, so if you provide a signal here, clock signal, RWL1, RWL2 with this width, pulse width, in circuit operation for case 0, 1 or 1, 0 or 1, 1 case, yeah, this red one is a case 1, case 0, 1, 1, 0. So if it is initially high and then comes down and settle here. If it's a case 1, 1, comes down quicker and settle here. So if you wait long enough, this is a no operation. You will get to no operation, see? 0, 0, for instance. And if it's 0, 0, you get this 0, 0. Yeah, 0, 0 is you get 1, 1 here. So you get 1. And in those two cases, you will get a 0 out here. So it's realized, no function. Now, on the other hand, to realize a NAND function, you make this pulse width half so that you have this scenario. So, you cut it off. So where green line, 1, 1 is fully realized here, the red one is sort of stopped here. It's still 0, 1, 1, 0 operation here. So that's sort of a NAND operation, 1, 1. So this can be, yeah, it's considered beyond some threshold is considered high. So yeah, it's 0, 0 is really high in NAND operation, but 0, 1, 1, 0, this is close to high. So roughly speaking, you are realizing NAND operation by adjusting this pulse width. So that's one example of a logic operation in memory, right? Yeah. So computing in memory, can memory provide performance breakthroughs for traditional architectures? The answer is yes. In memory, computing will achieve massively parallel multiply, accumulate, MAC operation. So it's if you use memory, it's a high density and thus low cost. Useful for matrix vector multiply calculation, as in a neural network or fast Fourier transform filter and the simulated annealing type of a thing. Simulated annealing is used in optimization, right? So in case you are not familiar with the simulated annealing, it comes back from a blacksmith art. I don't know whether you watched how blacksmiths make a knife, strong knife. They just have an iron core, put into oven, make it really hot, and bring it out. You hammer to flatten it in the shape of a knife, right? So you flatten it. Then you put it back to the hot oven, make it really hot, bring it out, push it down, hammer it again. So you repeat that process. That's sort of a annealing process. So in optimization, you do some crazy things like that. You heat it, and then you cool it down, heat it, cool it down. During that process, one can find the optimal solution without getting stuck in local minimum, especially in nonlinear optimization. So see, computing in memory by using memory operation, you can achieve the same thing. So this shows again crossbar array. Multiply function is done by Ohm's law, input voltage, and then here is a conductance, memductance, and the current flows. You add them up in the column, so it's a MEG operation. In terms of element here, you can have a resistive RAM, phase change memory, or spin torque transfer magnetic memory also. So this is published result back in year 2021, International Solid State Circuit Conference. They published a paper on 4 megabit resistive RAM 1T 1R, right, to prevent sneak current. They put transistor in series with a memristor here for CIM, and they achieved high performance for tiny edge computing application, edge AI device. And in terms of a figure of merit, it's increased by 3 to 4 times by using computing in memory. Now, this shows how you can save power consumption also. So if you have a non-volatile computing in memory, NVCIM, say originally you have a digital block, SRAM, and then you try to do computing in memory, that itself saves energy. But if you replace this SRAM to non-volatile memory and then do computing in memory, what you can do is you save this portion of power, this much energy. Actually, this is time and the power. So this whole red thing is gone. So weight data movement, that's corresponding to red block. And then the blue one is a computing. But by using non-volatile memory on chip, and then you do computing in memory compared to SRAM, you just end removing all this red block and only need this blue one. So this is additional saving in terms of energy and the power, right? So that's an appealing thing, using memristors on chip and doing computing in memory. And this is another data, hybrid CMOS resistive RAM chip technology at TSMC and others. And according to French paper, they had a CMOS chip, 30,000 CMOS transistors. They have a 2,000 hafnium oxide memristor on top of this CMOS. So you embed this memristor circuit on top of a CMOS. And by doing that, memristor run AI task. Power saving is almost 3 orders of magnitude. It's a factor of almost 1,800. That was published in January 2023 in IEEE Spectrum. So that shows really what has been done. In terms of throughput versus power, so trillion operations per second type of a thing, and the power in terms of watt. So this is a power, and this is throughput in terms of TOPS, right? And what you can see here is if you use H-transistor SRAM or the spin torque transistor MRAM or FE, ferro FET, type of a thing here. That's a star here. They stand here. Compared to operations here, which is GPU, and then red one is a digital ASIC, is cloud computing here. But here they are closed for each computing operation. So power is much reduced, and throughput is somewhat less, but it's better than here, for instance. This one is computing in memory RRAM macro using this one. So yeah, throughput here is falling behind here, but the power is much less here. So that's comparison. So CIM paradigm, right? So you have a layer 1, which can be neurons, and then layer 2, which is another neurons, and then this is memristive connections, right? All the learning is done in this way, connectivity here. So that's how you can have a crossbar array, and you feed input, and then you get multiplication and the sum. So that's I sum is a sum of all these individual current, which is happening based on Ohm's law, that is a multiplication. So multiply and accumulate, make operation is happening in this every column here, right? And that can be, each cell can be 8 transistors RAM, 1 transistor, 1 memristor, or 1 transistor, 1 floating this gate type of a thing here, right? So it's still a different scenario, but in this talk we are emphasizing 1 transistor, 1 memristor array type of a thing. Now, Professor Daniele Ilmini in Italy, he has given lecture on in-memory computing with the memristors and mem transistors. I think the first lecture or second lecture, somebody asked about mem transistor. Yeah. So I will illustrate this, his use of a mem transistor, and you will see what potential trouble for mem transistor is. So here, this is a mem transistor. And if you look at the current flowing between drain and the source, see, he is requiring lots of voltages, 10 volt, 20 volt, 30 volt, or minus 20 volt, minus 30 volt, compared to what is used to 1 volt or even below 1 volt. So in principle, it's good, but in terms of practical use, still far away, right? It's very, very high. And then here, he's doing operation between minus 20, minus 15 volt, and so on. And this is a corresponding current, and so on. So this is a configuration of a memristor here, a mem transistor, and this is a dimension. It's a 50 to 120 nanometer gap here, and so on. And this shows these conductance, right? Nanosiemens as a function of time, as also a function of a driven voltage here, which is high voltage. Now, the interesting thing is here. So this is number 4, sort of putting into 1, 2, 3, 4, 1, 2, 3, 4, 5. So it's a 4 by 5 matrix structure. There are about 20 grids. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So if you scan, there's nothing, 0, 0, and then 1 and the 0, right? So you have a 0. So starting from here, 0, 0, 1, 0. So time sequence. If you scan, you will have a pulse here. It's a spike type of a thing here. In this case, it's a 0, 1, 0, 0. So 0, 1, 0, 0. Here is a 1, 0, 0, 1. So 1, 0, 0, 1. This is a summit. Yeah, it's not quite, yeah. So this is 1, 0, 0, 1. So it should be 1, 0, 0, 1. And then, yeah, this one is 1, 1, 1, 1. So all the way 1. So 4 of them are 1. And then here is a 0, 0, 0, 1. Right? Yeah. So this is a 1. I think this is somewhat. So this is a 1, yeah, 0, 1, 0, 0. Okay, so this 1, 0, 0, 1, and 1, 1, 1, 0. So you converted this one into a sort of a spikes along the time axis. So this is like a signal on time axis. So there are 1, 2, 3, 4, 5 signals going into this MEM transistor here, right? Where this conductance can be changed, right? And that forms, so one node here, and then you have the memductance here, and then another neuron, and so on. So you can build the neural network using this, but you can code this pattern in this time fashion. So by doing that, you can have like a 1, 2, 3, 4, 5, 6, 7, 8, 9, and then this is a 0 pattern. So you provide this into neural network. You train them. If not matching, then you adjust the weight and all that. So you go through training, and at the end, the quality of that network will be, yeah, when you have the input is 1, are you getting really 1 desired output? If it's a match, this should be very strong. There may be some side component non-zero, but as long as this isn't dominant, it's good. 2, 2, 3, 3. So this is an indication how good the quality is, right? So this one case is very strong, 2 cases very strong, 3 cases not as strong, about the 0.8, 0.9. This is strong, 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 strong. Here, 8 was not as good, but still maybe greater than 0.8, and then 0.9 and so on. So this indicates that yes, you can have a correct identification by feeding after training these numbers. So that's how you train this in-memory computing with memristors and MEM transistors. So device property important for computing in memory, right? Device properties of high importance for computing in memory. On-state resistance. So we talked about in the binary case, on-state, off-state, right? 2 values. R1 is a critical parameter to determine the energy efficiency. R1 is in the range of 100 kilo ohm to 1 mega ohm. That is desirable if you can have a high resistance here. But usually in many publications, you'll see that this is much, much lower. On-off ratio, the higher the better. The small on-off ratio is not a big problem though. If you're using the dummy column or reference array to subtract off-state current. So there's some adjustment. If you do that, that can be overcome. Multi-level, if you have more than 2 level, multi-bit is desired for higher integration density. SRAM, MRAM is binary in nature, while other embedded non-volatile memories generally offer multi-bit per cell, 2 or 3 bits. Emerging non-volatile memory, 183 per cell, or even research-wise, 1,000 per cell is achieved. Retention mechanism that affect the retention include short-term relaxation after initial programming, the long-term drift, and so on. So that can cause some, a noise in a read process. That method for training, write voltage. Write voltage for many embedded non-volatile memories, including RRAM, phase change memory, or ferroelectric FET, are still in the range of 2 to 3 volt, which is higher than typical logic processor supply, 0.7 volt or 1 volt. Therefore, a level shifter that converts the voltage domain is needed. So, if you have this power supply, 1 volt, say, then in order to have a 230 without requiring additional power supply, you have an on-chip level shifter to generate that. Endurance. Training requires frequent write operations to the memory cells. However, it's often thought that endurance requirement is prohibited for today's non-volatile, embedded non-volatile memories for training. Turns out that endurance of 106 cycles is sufficient. I think that's a sort of an overstatement. Probably you need more than that. For most of the image recognition training workload, if you're using batch mode training. It is also worthwhile to note that the weight update is incremental. So incremental weight update, so just add or subtract type of a thing. The switching over is thus not fully between the highest conductance and the lowest conductance. That helps. Variation, device to device variation is tolerable to some extent if iterative training could be tightened with write verify for inference. So, yeah, it requires some more peripheral circuit to do this. So you write and then verify, see whether it's correct or not. Then you can overcome or mitigate some variational problems. Cycle to cycle variation is more problematic for in situ training, right? So when you keep on operating, then there is a drift. So small amount of noise injected into training could actually improve the robustness of DNN. So since it is a noisy process, by adding some noise in the training process, you make it more robust. So that's an interesting idea, right? The asymmetry nonlinearity is well known that asymmetry nonlinearity in the weight update curve are the most critical property that may significantly degrade in situ training accuracy. So in that case, algorithmic tricks suggest some relaxed requirements on linearity and symmetry, but realizing software comparable in situ training is still quite challenging because you have to operate in software domain for a complex data set. Alternatively, hybrid precision synapse design were recently proposed, which leverages a volatile capacitor for symmetric and linear fine-tuning and non-volatile memory component for coarse tuning. So there are some techniques to mitigate such non-linearity and asymmetry. So people are working on it, which will make more complex. But even DRAM, SRAM is quite cumbersome to design operational DRAM or SRAM. So this shows a statistical variation in memristor characteristics. So you have an array of memristors, crossbar array. You have a measurement, but there is a variation. See, it's not single line. And this is statistical distribution here. And so you needed to be aware of variations, and that's a practical reality. But there are, you will see in this lecture also some technique overcome such variations, mitigate such variations. We went through this comparison of phase change memory, resistive memory, and the magnetic memory, and how they compare in terms of area, CMOS compatibility, ratio between high resistance and low resistance state, speed, right? And then energy consumption, endurance, and then retention, and then voltage required, and the number of states, and so on, and then stochasticity, randomness. So this is that scenario again, and this is array, and in this case is D2A, A2D is involved here, but one way to overcome this thing can be either shared or you can have a pre-charged sense amplifier circuit. And this is also comparison of a static RAM versus a resistive RAM acceleration and how they compare in terms of number of bits and the energy efficiency. So yeah, so you can see that the SRAM is better performance, right? SRAM compared to RRAM, which is here. But in terms of packing density and so on, it's much better to use RRAM, for instance. Also, we talked about the Hebbian learning rule in neural network. The Hebbian learning rule proposed by Donald Hebb in 1949 is one of the earliest and the simplest learning rules in neural network, primarily used for pattern classification and unsupervised learning. The rule is based on principle that connection between two neurons is strengthened if they are activated simultaneously. It's called neurons that fire together, wire together. That is the principle of Hebbian learning. It doesn't talk about precisely the timing, but we will discuss that timing matter. But in principle, generally speaking, neurons, two neuron pairs that tend to fire together, then the connection between them is strengthened. That's the principle of Hebbian learning. So this is a Memristive synapse, and how you do the voltage programming, and the conductance increase between them. And this is interesting one. This is used a lot. Depending on presynaptic pulse neuron signal, postsynaptic neuron signal, and then when you compare this timing of them, say at the peak point, the timing difference is called delta t. Sometimes pre-synaptic signal is ahead. In that case, delta t is positive. But sometimes post-synaptic action potential signal can be ahead of the presynaptic. In that case, it's negative. So when they are close, this time difference is close, meaning that they tend to fire together. Then learning, the inductance increase is high. This is a change in the weight. So weight change tends to be higher when delta t in magnitude is small. When it is a high, signal is far apart, then yeah, the change is not happening, right? So in terms of you cannot really have a precisely zero. So many papers mention about this type of a curve. It's almost 1 over x type of 1 over t type of a curve here. But what about when they are zero? Actually, shouldn't happen anything. So usually you connect it like this, right? Because when they are coinciding together, if it really happens, then it may not happen. So this shows that aspect actually. If they do the really study and then simulation and the measurement, is we are going through this origin here. So there is some short-term spike timing dependent there's a learning rule. There's a weight change is a function of delta t, timing difference, right? According to Hebbian learning. And it can be very complex. It's delta W weight change. When it is a positive, right, you have some exponential function multiplied by constant plus some other exponential function. If it's negative, a negative exponential function, and then this term. So it can be very complex. So people have tried to realize such a weight change. Can you turn off that background noise? So potentiation is a positive change. Depression is a negative change. So to realize both functions, let's say potentiation is this circuit, depression is this circuit, and this is a additional circuit here. So if you do that, implementation of memristor synapse in lieu of a very complex CMOS synapse, if you replace a whole thing by one memristor, this is not really accurate, but nevertheless, as a good approximation, not using this. Imagine using this one in the neural network, how complex that can be for synapse. So, it's making sense to use a memristor. In terms of area difference, it's a factor of 300 when you do that. So this shows why 300, for instance, memristor versus CMOS circuit. So that's sort of a advantage of using memristor as a synapse instead of this complex CMOS circuit, right? And a CMOS plastic synapse. This is another version of a CMOS circuit. Again, many transistors, although less than the previous one. And that's sort of a crossbar array again. And the synapse also in series with the MOS transistor. The programming is important, right? For memristor-based neuromorphic computing, because you want to program this memductance or conductance of a memristor here, right? So this is algorithm, current state of conductance, and you predict prediction programming, voltage and the cycle. So say you want to change, so you predict what voltage do you need and how many cycles you need. And then you select rows according to required voltages, evaluate and all that, and then see whether you achieve it. If not, you go back and then predict again and until it converges, right? So you do algorithmically. So usually that computation is done off chip, and then once they determine, then they program and then apply to the chip to potentiation or depression, reduce weight from initial state. Right? And this shows comparison between total number of programming reading cycles of implementation of this neural net with and without calibration of a memristor model. So yeah, so the message is if you do calibration of a memristor model, you can do much better job. Compared to without it, the number of cycles 10 to the 5. So this one is like 2 times 10 to the 5, right? It's about 0.2 million, whereas this one is 3 million, for instance, and so on. Here, analog neural computing with a super resolution memristor crossbars. So, due to variation, statistical variation in crossbars, there is a concern, how do you mitigate such variations? And then this paper by Alex James and Leon Chua, for which they got Best Paper Award from TCAS1, is using many memristors. So they reduce relative current errors with increase in memristors per crossbar node. So instead of using just one memristor, you use many. Show improvement in the precision and accuracy of crossbar MAC operations. So yeah, you pay for it. You increase the number of memristors, but you reduce. So this shows one memristor scenario, 1M, right? The error can be 15%. If you use 2, error can be reduced to below 10%. If you use 3, 5%. 4, maybe 4%. And then if you use 6, it falls down to about 2.5% and so on. So yeah, you pay the cost in terms of number of memristors, meaning that less packing density, but you achieve a higher precision, and the computation result will be better by doing that. Now, this is one of the early result, right? This is a well-known paper by IBM folks, Jeffrey Burr and his colleagues at IBM Almaden Research Center in San Jose, California. They published this one, many years back. This paper is about 10 years old. And it's an experimental demonstration and tolerancing of a large-scale neural network. So they, in this experiment, they have 165,000 synapses using phase change memory. Yeah, so they use the phase change memory as the synaptic weight element. And in the nutshell, they both the experiment and the simulation, and in terms of a training epoch, 1, 2, 3, etc., they achieved almost 80% accuracy by doing that. Usually you want to achieve more than 90%, but in early stage, they did achieve 80%. And then they were handling both negative weight and positive weight. So they sort of repeated the column twice, and then they had some summing circuit to make it either positive or negative type of, depending on this weight. So some can be positive or some can be negative. So that's how they handle it. This shows that neuron circuit, you have an input multiplied by weights coming in, you summed up, and then you have a threshold evaluation here, F function. So if beyond that, output comes out, for instance. So they had I think it was 64 by, 24 by 26. So there is a 528 pixels. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it has a 24 by 26, I think, grid. Multiplication is 528. So 1, 2, 3, so that, and then you provide also 1, 2 layers and then output. So 10 output neurons, because there are 10 numbers, right? 0, 1, 2, 3, 4, 9. And then here is also pixel. So you have all these different weight, and there are, how many weights? 165,000 weights here, all this thing. So they trained all these weights, and then did sort of checking, and then they achieved about 80% accuracy. So it's one of the early papers cited a lot. And then you can have a neural network for EEG pattern recognition. So this is a neural network, a pre-neuron input coming in, synaptic network here, post-neuron, and then decision logic, and then make a decision. This is a hardware implementation, and it was applied to them, right? Now, this is done in collaboration with the professor at Sungkyunkwan University in Korea and UC Santa Cruz. My group was published in Transactional IEEE Cognitive and Development Systems, August last year. And this is about what is called sound localization. So see, suppose you have a human being here. If a sound source is right in front, the sound traveling to the left ear, right ear will be same. So if a system is correct, then it will say angle is 0. But if a sound source is all the way here, the distance traveling to right ear is shorter than distance traveling to the left ear, right? So if a system is correct, it should say that this sound source is from here is about maybe 45 degrees. So that's the idea. So if a sound source is here, and then this is the angle here, so it should come up with an angle here. So then, what type of precision can you have? That is determined by using memristor. So what is happening in this the path from left ear, right ear, signal comes in. It goes through this in a path which is like a delay line, and then a neuron is here in between. So there is the weight and then all this thing. So you can come up with this network like here, and then train it with the test signal, come up with something here. So in this particular case, it's corresponding to 120 degrees. So from here, maybe it's this may be a 0, and then all the way. So it's if you look at this, all the way to the left or all the way to the right. So it's a 90 degree to 180 degrees. So in this particular case, you see after all this simulation result, there are some noise, but there is a significant peak here. That indicates that the sound source is 100 degrees, 20 degrees. So that's there are about 180 neurons in this particular case to cover this. And what happens is neuron number 120 produces the highest spike. Then you know that it's 120 degrees, for instance. So that is the idea using memristors in this case. So it's a spiking neural network, but memristors in it, and then do that. So this shows more biomimetic spiking neural network based on monolayer 2D synapse with a short-term plasticity for auditory brainstem processing. That's the title of the paper. And this is the paper here. Biological model was used. Some model used pure tone with noise, and the frequency range 1 to 500 hertz, and the azimuth angle minus 90 degrees to 90 degrees. Resolution is 1 degree. It's very good compared to the other earlier works, 30 degree resolution, 10 degree, 5 degree best. But this was 1 degree resolution. Accuracy was almost 99%. Energy is only very small, 0.1 nanojoule type of thing. So that was a very exciting work using memristors. So once you do that, you can implement that hardware into mouse robot, and this mouse can trace where if you move this sound source, mouse will follow to that using that. So this shows the publication citations and memristor per year. So earlier I mentioned that. So since 2024, which is less than 2 years now, more than 11,000 papers. So its number is keep on increasing. So there are a lot of people, chemists, physicists, biologists, they are working on neural networks. Dendrocentric learning AI using dendrite like nanoscale device for sparse 3D integration. So here, for instance, a number of neurons, human brain has hundreds of billions of neurons here. If you use a dense 2D or a dense 3D, you don't quite get that. See, energy level. You cannot achieve this energy level. But if you use a dendrite, that's the hope that maybe you can achieve that one. So that's why there is a 3-dimensional integration interspersed layer of switches and wires. That's the structure. So it's a stacked crossbar, 3-dimensional crossbar, to mimic dendrite operations instead of a synapse, for instance. Memristive-based neuromorphic vision. It's an early paper by Jay Eshraghi almost 7 years back. So microprocessor will take a 2.2 milliwatt. This Memristive-based system will take a 7.8 microwatt. So tremendous, almost 3 orders of magnitude difference here, right? So that's also interesting application. And then a Spike GPT instead of a Chat GPT. You have a Spike GPT produced by the Jason Eshraghian's group. Luigi Zhu is the graduate student doing a wonderful job. He's from China. And he developed all this software and so on. And this is application. It's really, so what do you think of me? I ask. And then this is produced by ChatGPT language model. And by doing this, another thing is a scalable matrix multiplication free language model, reduce the compute cost. So idea being that instead of a megawatt of power, maybe you can use a light bulb watt, less than 20 watt. So eliminating the most computationally expensive element of a large language model, mainly the multiplication. By using different things, you can avoid the multiplication, thereby reduce power consumption to light bulb scale. This is very exciting one. I received it very well. So they published in June last year, about a year ago. So this is Spike GPT and so on. This is a hardware, field programmable gate array hardware for matrix multiplication free language model. So, they for 515 tokens per second. So at 21, 23.8 tokens per second at 13 watt, for instance. So it's a very, very exciting application. There are some hardware, NVIDIA Pascal hardware, Google's Tensor Processing Unit, Movideo's Phantom Unit, and so more and more hardware come. NVIDIA stock went down when China announced the DeepSeek hardware. So then now it's coming back up slowly. But that shows the international competition in AI market, right? So hardware really matters a lot. Now, so the next topic is, can we build a brain scale neuronal network? So this is a Hodgkin-Huxley model that generates action potential. So I told you in the first lecture, or second lecture, we identified this sodium channel, potassium channel back in 1976 as Memristive. And then year 2012, Leon Chua also published a paper in Chaos Journal on explaining chaos generation in local activity area, edge of chaos, and that sort of thing. So looking into basic, leaky, integrate, and fire network, right? Leaky, integrate, and fire neuron model is like here. You have a run resistor, DC source for resting potential, and the capacitor. So current comes in, it charges capacitor, and then it gets discharged. So you can say, for simplicity, let's assume that this is 0. Then you have a RC parallel circuit. Current comes in, charge up, right? A current pulse coming up, and then it's a pulse decay like this. So that's mimicking this pulse here, action potential pulse. So in order to generate that, you need some overhead, logic overhead. So you have a RC circuit, you have a current source coming in, right? So it can be, in this scenario, either this one or current pulse like this. So you have a constant current source and the switch to control what is fed into leaky model. But then, in order to, so you can, output in terms of the current charge up, right? And then maybe reaching some threshold value, and then must discharge to repeat the second phase and so on. So for that, you need some circuit, additional circuit, to make a decision. Hey, is the voltage across capacitor greater than threshold? If not, you keep on going. If it is yes, then you turn this switch on to quickly discharge. That's how it comes down, right? And then you turn this one off so that when next pulse comes in, discharge it again, and reach the threshold, then discharge. So there is a logic overhead here in this leaky integrated market. See, people discuss this without discussing logic overhead. So in that regard, this is not autonomous. It should be autonomous. Now, more complex cases, even more. If you want to go down and then rest and so on, then you have a reset and the set type of a thing. So you have a more complex overhead. You have to monitor two different threshold values and then generate a spike and the reset type of a thing. So overhead is huge, very complex logic overhead to replicate things like this. See, this is not just going up and then coming down to the, it has to come down and then rest the period and so on. So if you want to do this, then you need this type of it. It's very complex. Overhead is very large. It's no longer very simple. So how do you simplify that? So how can you use memristors to create neurons? So there has been many papers on this. MART memristor neuron, neuristor neuron, which has two memristors, two capacitors, and then an RC circuit, and then DC source and DC source. And a diffusive memristor-based neuron, that sort of thing. Threshold switching memristor-based neuron. So there's a special detection and then special kind of memristors also. But let's look into the action potential, really, what is happening. It starts at rest potential about minus 70 millivolt. And then when there is a stimulation, it rapidly rises up to all the way to 30 millivolt, reaches some threshold, and then quickly discharges. It's called repolarization. And then it goes below this level, hyperpolarization here. And then it increases slowly to reach this level, resting potential. So that's a really accurate action potential. That's a biological case. So what is happening here is activation of sodium potassium channels. So that's happening there. So can we do this? So what does it take? So this shows more dynamics, right? So resting potential minus 70 millivolt goes up. So sodium channels open here, goes up, right? And then sodium channels close down, and then potassium channels open to bring it down, right? And then it closes here, and then goes up to that. Yet, original Hodgkin-Huxley model proposed a sodium channel, potassium channel. So what can you do using memristors? Can you use memristors to generate this one? So that's the sort of a message here. Can you do that? So this is scale is 1 millisecond. See, this is about 1 millisecond, 2 milliseconds, 3 milliseconds, 4 milliseconds, 5, etc. So we looked into this. What if we have just this circuit, replace resistor with the memristor here? And suppose memristor has two states, off state and on state, right? Because in terms of hardware, no memristor has a similar characteristic like this. So you can have a off state, and then as you increase the voltage, it reaches threshold, jump up to on. If you decrease, you stay on, and go all the way to reset voltage here, another threshold, it jumps up back up, and then increase, so it repeats like this. So suppose you have an IV characteristic of this nature. It's here, goes up, that's off state, and then once it exceeds the threshold voltage here, millivolt, jumps up and becomes on state, R on, low resistance state. It comes back up to like this. This is coming from a real device measurement type of a thing. So if you do this and simulate this, you can generate a pulse like this, go up, it comes back up like this. If current waveform is like here, for instance, and then the voltage becomes a red signal like this. So interesting, right? Because you have a E-rest potential. So this is minus 70 millivolt. If you put this is 0, then you don't need it. It will be 0 volt, and then this will be like a 120 millivolt type of a thing. Now, we don't quite get that. So what we want is we want to get this negative thing. So rest potential, and then hyperpolarization, and then do this sort of a thing. So for that, we need two memristors. So we have a one reset voltage, one E-rest potential. And then a current comes in, and this is a voltage across capacitor. So what is happening? You can see that one memristor is on off, and another memristor is a switch on and off. And that is going to be controlled by voltage across the capacitor. So it's autonomous, but it can generate this sort of a pulse autonomously without any external circuit. That's the beauty, see? Because memristor has a switching capability itself, right? As we saw here, memristor can switch if you, depending on voltage signal going up and come down. So you can actually, without looking into, you got a hint from Hodgkin-Huxley model, but you cannot realize a Hodgkin-Huxley complex equation with a memristor. But if you use a commercial memristor, you can do that. So we used a commercial memristor to generate action potential like this, using two memristors and two DC source with a capacitor. So this was published in a paper by Kang et al., my graduate student, colleague in Germany, colleague in Italy. Alan Escali was involved in how to build a memristor integrated and fire model for spiking neuronal signal generation, published in TCAS 1, December 2021, for which it was recognized with the Darlington Best Paper Award in 2023. So MIF for neurons, memristor synapses can potentially realize a semiconductor brain in the same area of a human brain with 20 watt. That's an exciting novel story, right? Because a neuron you can realize with a memristor, synapse is memristor, so everything can be memristor. So that's the idea. So can you really do that? Well, it's a pipe dream, but anyway, this is experimental measurement. That was a simulation using known memristor, existing known memristor. So if you measure known memristor characteristics like this, see, it has a high resistance state and low resistance state. This is a threshold, and then another threshold here to switch. So by using this hardware implementation with the voltage source replaced by Thevenin's equivalent circuit. So this is corresponding to current source converted to voltage source scenario. And this is a MIF, Memristive integrated fire neuron model. And we were able to produce this sort of action potential. See, look at this. Going up, and it comes down, go below the resting, and then approach the resting potential, and so on. So that's the exciting aspect of it, right? So what can you do? So if you have a neuronal circuit, you have a neuron, axon, and then a synapse, right? So you can have a multiple input to the neuron, say, another neuron number 1, another neuron number 2, another neuron number 3. They send the signal to the synapse, and then this is a neuron, integrate this one, and the threshold logic and the output, and then give fan out to send the signal. Actually, the difficulty is a neuron sends the signal to thousands of other neurons. So it's not fan out of 3 or 100, it's 1,000. So does a neuron have that much power without the buffer, for instance? That's a big question. Turns out that it's chemically, biologically, along the axon, it sort of generates the input, embed energy into that signal. So that cannot be replicated by electronically yet. But biology has some magic in it. So suppose you do that. See, you have 3 neurons, 3 synapses, 1 neuron, and the output and the fan out. That circuit can be realized into this Memristive layout. So this is an input current line, and then this is a DC source, E-reset battery. See, if you go back, we had that one, right? E-reset. So we have a DC battery line here. And then we can have a Memristive formed here in series with the battery. And then the fan out, right? So fan out to I2, fan out to I3, fan out to I4. So you can just have one column of memristors in nanoscale. So if you have a 3 nanometer wide wires, top and bottom, this takes only a small area. See? So very compact layout for this neuronal circuit. Of course, you have billions of them. It's very complex. But I will show it to you that there is a potential for realizing such a thing. But before that, we want to test this MIF model neuron, whether it can do the job, for instance. So spiking neural network with the MIF neuron and the Memristive synapses, which allows the smallest area, lowest power, highest accuracy analog configuration. So you embed this thing, so spike signal comes in, and then neuronal neurons, and then synapse, and the neurons, and all that. So you have a network here, and then you have a test pattern, MNIST, the number test patterns, right? 60,000 images and 10,000 are tested in MNIST benchmark. And you apply this technique, it's just like a 28 by 28, just 784 pixels. So, you have a 784 neurons vertically. So compared to other things here, this particular work, using 3 layers actually, 784 neurons, and then next is 100, and then 10 neurons. So this is a very not so deep neural network, analog operation. It can achieve 93% accuracy. The additional complexities are very low, whereas the other work involve high overhead because you have to have external control to monitor threshold and all that sort of a thing. but switching is happening by memristive itself. So that's very promising in that regard. And this shows some additional benchmark. Pattern recognition, rectangle, X, diamond, and triangle type of a thing, and the learning, and then level of achievement type of a thing. And then there is also two-dimensional material memristive synapses. So a lot of people are in materials looking into this, using 2D material to have a synapse operation. And then this is a collaboration with IIT Dhanbad on emulation based. So this is a CMOS LIF neuron mimicking MIF thing using CMOS circuit. So this is a CMOS neuron and applied to pattern recognition. Ballpoint pen, light bulb, a man standing on, and dog and bus, that sort of thing. And this is a circuit to do the job, and this shows identification after a time, whether it's a pen, bulb, a human, and the tree, etc. So that is also very exciting work. CMOS memristive emulator cross-boundary based object detection and recognition, published in Transactions and Circuit System 1 as a regular paper. So those at IIT Dhanbad, it's right next door to you or in the same group. Detection. So this is a sort of a temperature measurement. See whether you can do so. 90%, 80%, and case is true. So that's exciting also. And then the other one is a CNN, cellular nonlinear network. Cellular, not neural network, but this is a cellular nonlinear network. Each node here is implemented by this circuit here. This is L08's work, published in 2021. And in this module here, you embed memristive here. And this is a complex state equations. And it turns out it's a very, very fast way to do this. So, you have this as a test case, flower pattern. If your desired operation is to invert this pixel, convert dark one into white and the white one into dark, this is what it does. See? So, yeah, simulation of an M/N store, memristive CNN, and use 145, yeah, and then and it's 147. That's the array size and all that. So this was designed system theoretic method for designing bio-inspired MEM computing memristive cellular nonlinear network. So it was published Alon, Ronald Tetzlaff, and myself, and Leon Chua. So yeah, this was also very exciting work here. And in fact, Ronald Tetzlaff applied this for iron metal melting process, and he can watch how iron is being melted and then being formed. So it was an industrial application for doing that, using very fast, ultra fast image processing, using a memristive cellular nonlinear network. Memristive cellular nonlinear neural network design analysis application. So this one is to say, find the horizontal bar. So yeah, it in this case is this bar is replicated here. This is too short, so this bar is replicated. This bar, and this bar, and then this bar, and so on. So you can do this very fast. The license plate recognition, for instance, A8888A. So memristive based one. Output of B is MCNN. And the traditional CNN output is like this. So it matches, but it's much faster. This so we talk about the variation, right? So the question is, oh, if 1T, 1R has a variation, can you use a 2T, 2R? All right. So that's interesting work done by French group, LETI, this research institute, and the resistive memory in back end of line between M4 and M5. So they fabricated this one, 130 nanometer CMOS logic process. And this is a 2T, 2R array. And then apply this. And this is a processing. They did a processing between level 3 metal and level 4 metal. And had this Memristive implemented there and for demonstration. And then this is an analog artificial neural network chip with 2.4 billion Memristive in 2019. Was published, 2.4 million Memristive. Commercial analog matrix processor, see? Commercial analog matrix multiplication processor. So this Mythic is Mythic, I don't know which one is correct. It's a startup company. They have 80 million deep neural network weight parameters. See, it can allow up to 80 million deep neural network weight parameters in this box. And performance and power efficiency, single chip provide up to 25 TOPS, tera operations per second for compute power, 3.3 to 4 watt, running typical complex models, 10x power, lower power than comparable digital solutions. And there's a module available from this company. Commercial neuromorphic chips, there are companies, Intel Corporation, Loy High, 128 neuromorphic cores, 14 nanometer technology, IBM True North, 1 million spiking neurons, 256 million synapses, 64 by 64 cores, 5.5 billion transistors. It consumes 70 milliwatt power. Qualcomm, Brain Chip Holdings, Samsung, NVIDIA, General Vision, ST Microelectronics, global chip market, Huawei Technologies, their share is 82 billion, IBM 62 billion, NVIDIA 60 billion, 61 billion rather, Brain Chip 56 million, Intel 55 billion, Qualcomm 39 billion, ST Microelectronics 14 billion, Samsung 7 billion, General Vision 22 billion, Infinera, don't have a figure for that. But it shows some activities, right, in neuromorphic chips and performance of AI engines, the inference versus results. So this shows see, total number of GPUs. So if you have a bubble size big, you are using more GPUs, for instance. And it shows the state of art, medical imaging and object detection, image classification, local, large language model type of a thing here. And this is AI chip, wafer scale integration. This shows wafer scale. So this is a case where they have a 4 trillion transistors even. It's an updated number. Can train artificial neural network with 24 trillion parameters. 24 trillion parameters. This is as of March 13, 2024. It's a tremendous number, isn't it? And this is a AMD M1325 based system, which is on par with the NVIDIA H200 based system. So AMD is competing with NVIDIA. And NVIDIA is doing very, very well. but AMD is also doing very well. These days, Intel is not doing as well, but they try to catch up. Three-dimensional hybrid CMOS memristor integration. So this shows this Intel product, right? And then this shows the state-of-the-art three-stacked nanosheet transistor. So this is like a nanosheet to form the gate area, for instance. And the SRAM cell density, megabit per square millimeter, 2020 was 17, 2028, 37, 2034 is supposed to be 142. So it's like a 4 times increase. NAND to density, 20 is 47, right? 47 megagate per millimeter square. 28 is 1.7 times increase. And 2034 is almost 330. So 4 times increase and so on. So NAND, flash chip is very, very compact. In terms of speed, is good, but NAND is very dense. So that's why they use NAND operation. This shows a gate all around transistor. See, it's an individual gate tied together. It's all gate all around. See, this one is a bigger gate all around. All around. 2D memristor synapse ultra dense integration. So I mentioned this earlier. So here is the analysis, right? Can we reach brain scale memristor artificial neural network, for instance? So let's look at some numbers. Number of neurons is 10 to the 11. Number of synapses 10 to the 14 to 10 to the 15. Surface area of median human brain is 2,400 square centimeter. It's like a handkerchief. Your handkerchief, when you unfold it, that size. Volume, in terms of a volume, is 1,000 cubic centimeter. So that's the brain. And can you come up with some artificial memristor network like this of a size of brain? And if we have this neuronal circuit, as we indicated, using memristor neuron and the memristor synapse, we can come up with one column to realize all this with a fan out of 3. But the problem is it has thousands of fan out even. So how do you handle that? That's a good question. But if you do simple mathematics, the area occupied this sort of a neuronal circuit for this number of synapses and neurons, if you calculate this in a 3.5 nanometer minimum feature size, this whole area, including 10,011 neurons, 10,015 synapses, and some guard bending. Instead of 50, you add guard bending over 20 because of interconnected area and other things. Still come below 2,400 square centimeters. So physically speaking, if you can realize a neuron using memristors and the synapses, you can squeeze all the elements into human brain surface area. That's the message. But does it function like a brain? Well, that's a big question. You need probably software to operate this thing. And you probably need still some supporting logic, which requires some CMOS type of a thing. So that remains to be puzzled. But on the other hand, memristor can be also used for logic operation. So it's open, wide open for future investigation. So this is a roadmap for memristive AI system for the future. So this is a memristor hardware, memristive neuromorphic system, 2D, 3D hybrid CMOS memristor integration, application software, open source hardware type of a thing, or a software as well. Then you can build this, a cyclic thing, S-curve, right? S-curve to make a progress up and up and up to increase the level of artificial intelligence. And this is one scenario, maybe humanoid robot which can communicate, wireless communication with the big database and so on, can help this archaeologist to do the archaeology project. So this is a J. Park robot archaeology. He presented this paper in Seoul this year, 19th International Conference for Korean Society of Museum Studies, where robot can help this archaeologist, even guide to find where to this. This is sort of a pipe dream. That's the end of this talk. This is again our campus, Monterey Bay. Our campus is like a state park. So tall redwood trees, lots of open area, and the engineering campus is somewhere here. So now that's the end of my talk. Now we are open for questions.
Okay, thank you very much, sir, for your deep knowledge in this area. Please, attendees ask question if anyone having any questions regarding this lecture. This is the last session of Kang sir for this course.
Right. Yes. So it has been a pleasure to be with you. And my sincere hope is sort of you got good starting point to learn about memristors and its application for neuromorphic computing. It's just a beginning. And I think a lot can be done in the future. It's wide
Yes, sir.
open.
Yes, sir.
Yes. So please study. Yeah. Any question? No question. Huh?
Sir, there is one question from our side. One of our scholar will ask question.
Yes.
Sir, in PPT number 289, sound localization, so PPT
Yes.
number 289 in sound localization,
Right.
slide. So their sound only make the intensity of the sound or the frequency of the sound we can measure.
So 289 is 289.
Yes, sir.
89 here.
Sir, here we take the intensity or the intensity of the sound or frequency of the sound here.
So intensity is assumed to be, I don't know what level was, but yeah, frequency, we showed that it can handle different frequency range, I think. We may have some statistics. Let me see.
Sir, we do some mathematical analysis like short-term Fourier transform or MFCC. We need for this particular applications.
No, it's based on this delay element and the conductance, that sort of thing. Yeah.
Okay, sir. Sir, it only provide only degree. From which direction it will be sound will become.
Yeah, it's right now it's azimuth, but you can also do extend it to vertical direction as well. Yeah.
Okay, if you go for the 360 degree, then we have take the crossbar array of two crossbar array, means two array of neurons for
Right.
the different intensity of sounds coming from for different direction. So it will be suitable. So
I don't know. Maybe I think assume certain level, but if it is too weak, then probably cannot do the job. So I think assume certain strength. Yeah.
okay. Means there are certain constraint about the.
But on the other hand, you can amplify incoming signals, right? You can amplify incoming signals and provide a stronger input.
Okay, sir. Sir, one more questions in page number PPT number 270.
270.
Yes, sir.
270. Let's go. 270. Yes.
Sir, here, sir. What type of circuits means you convert the pixel into the pulse. So it is a mixed signal design or purely analog circuit, sir?
Well, you can say this is a mixed signal, right? Yeah, so you need a conversion. That's a sort of outside to provide the input. So that is a given, right?
Okay, it is mixed signal circuit. So it is applicable for real-time application for video processing?
I think so. I mean, you have to ask the speaker here, but I
Okay,
think
sir.
they can apply to real time application. But the concern here is this one, this high voltage here.
Yes, sir. Yes, sir.
So there is 2 more queries in the chat box. You can check it.
Yes, so I have the Vaishnavi's question. Instead of applying stimuli to 2 separate devices for STDP measurement, is it possible to positive pulse and the negative pulse separated by specific interval within the same device? You have to have a neuronal like a signal, right? So it has to be in that range to have a proper operation. So neuronal signal is in real biological system minus 70 millivolt to positive 30 millivolt. But depending on the memristive characteristics, this set voltage, that range, you can operate the voltage level according to that device. So you have to know the device characteristic and then set the amplitude of signals, right? Yeah.
Okay, thank you very much, sir. There are no more queries, and we are really grateful that you have took so many interesting about the memristor and its application on the neuromorphic field. So today we will end this session, and this is your last lecture. So many thanks, and we wish that your health will be good, and if you arrange the new course in the future, we will try to invite you again, sir.
Thank you so much. It has been pleasure to be able to serve you. And myself, the teachers, they always learn while preparing
Yes,
to
sir.
teach. So I myself had to review many papers to come up with these materials. So it
Yes,
was
sir.
a good
Yes, sir.
investment. Yeah, it was a good learning
Yes, sir.
experience myself. Yeah, I don't claim I know everything, but it was good to review literature. So as you can see, there are many updates like data available this year, 2025, March, April, etc. So it was a good opportunity for me to review and get organized. So thank you for the invitation. Thank you for your attendance. And hopefully you learn something out of this lecture. Thank you.
Thank you, sir. Thank you.
Okay, bye-bye.
Bye-bye. Good night, sir. So this is the last lecture of this session, and of course this of the course also. We will have one test from 3:30 p.m. which will be for 1 hour duration, and there are 30 questions of MCQ based. We will share the Google link for that at the when the time comes, sharply at 3:30 p.m. So please be prepared mentally, and so that you can attend the test, because without attending the test we will not distribute any certificates. So you need to give the test. After that, based on the marks, we will distribute the certificates. And also there is one feedback form you have to fill up. We will within a minute or within 10 minutes we will share in your WhatsApp group. So please join WhatsApp. Don't leave WhatsApp group for 10 days at least, because we have to distribute all the materials related to GAN course also. So don't remove from yourself from the WhatsApp group, and we will share the applicant feedback form within a minute. Just get a printout of that one and fill with your hand, and then scan it and upload in a provided shared link, Google link. Okay. So you must have to fill this feedback form.
Then you will get to the certificate.
Then only you will get the certificate. That means you have to process, follow all the process related to GAN course. You have to fill the feedback form. You have to take the give the test also. Otherwise, we cannot give the certificate, because we have to submit all the data, relevant data, to the GAN coordinator also, authority also. So thank you very much.
To take a printout, sir.
Yes. Or one more option, if you have a pen tab or pen touch device is also there, you can just fill that PDF and get a scanner. You can upload in the Google link provided. Not necessary to get a printout. If you have a pen tab or pen tab device, then you can do that.
Okay,
Okay.
sir, thank you.
Okay, but you have to give your signature also in that form. Okay. Thank you. We are leaving now.